Roanoke Approach Control, this is Cessna 2666 Lima, approximately 30 miles east, VFR. Request your weather, over.
Cessna 266 Lima, Roanoke Approach Control. Roanoke weather measured 4,000 broken, visibility 5 haze. Wind 160 degrees at 8, altimeter 3010. Visibility lower south.
Cessna 2666 Lima, roger. I'm at 2,500. It's getting pretty hazy. Request radar assistance for Roanoke.
Cessna 66 Lima, are you transponder equipped?
Cessna 66 Lima, negative, no transponder.
Cessna 66 Lima, I show no radar target 30 miles east.
You may be below radar coverage. Can you climb to a higher altitude and maintain VFR?
Cessna 66 Lima, affirmative. I can make it to about 3,000 and maintain VFR.
Cessna 266 Lima, roger. Report reaching 3,000. Maintain VFR.
A low ceiling, mountainous terrain, and an anxious VFR pilot.
Cessna 66 Lima, Roanoke Approach Control. Cessna 66 Lima, Roanoke Approach Control. Do you hear me? Over.
Cessna 66 Lima, affirmative. Just approaching 3,000, heading 270.
Cessna 66 Lima, roger, thank you. Cessna 66 Lima, I'm starting to paint a target 25 miles southeast. Turn right heading 330 for radar identification.
Cessna 66 Lima, roger. Turning to 330.
Cessna 66 Lima, Roanoke Approach Control, radar contact 25 miles southeast of the Roanoke Airport.
It's a good feeling to know you're on radar. That radar's all-seeing eye has found you and will help guide you to your destination. But then radar has been around so long that we take it for granted. The mystery which once surrounded radar has gone, and the giant turning antennas and bright scopes are now commonplace.
6 northeast.
Radar is great. We've learned to depend on it. But the problem is that like so many good things, we tend to become over-dependent on it. The result sometimes is a compromising situation where radar can't help due to its limitations. Admittedly, we don't yet have full coverage at all altitudes and in all areas. And as good as radars used in air traffic control generally are, they are not perfect. The point is that radar controllers can't guarantee to get you in every time. A pilot's responsibilities still hold, even with assistance. Fortunately, we don't all have to become radar experts in order to use its services. Often, radar can help us in spite of our lack of information. However, understanding the fundamentals of radar can enable us to utilize it more fully and intelligently. The kind of radar equipment used in air traffic control can be described in simplest terms as a high-frequency radio transmitter broadcasting high-energy short radio waves through a rotating antenna. The name radar comes from the World War II acronym for Radio Detection and Ranging. Radar works on an echo principle. So much energy or power is transmitted that when it strikes a radio reflective surface, enough of the energy bounces back to the antenna to be picked up, amplified, and fed to a display called a scope, where the signal registers as a bright blip or radar target. The scope is a cathode ray tube similar to a television tube. The type of radar most useful for air traffic control is designed so that the signals can travel a two-way street. Therefore, the transmissions are made by alternately turning the transmitter on and off repeatedly in mere fractions of seconds. The return echoes are received and processed during the intervals between transmissions. This allows the system to utilize one antenna for both sending and receiving and still look at a number of targets simultaneously. The reason that a radar can show distances so accurately is that the signals travel at the speed of light, so that the length of time it takes for an echo to return shows precisely how far away the target is from the antenna. The rotation of the antenna and the sweep of the radar scope are synchronized, so that when a target is painted on the scope, it shows the exact radial of the target. What the controller sees on the face of the scope represents a long, overhead, two-dimensional view of the airspace covered by the radar. The center of the rotating sweep represents the position of the antenna, and the scope face is calibrated to show distances. A map is incorporated into most present systems to allow the controller to identify geographic points, locations of navigational aids, airports, and other facilities. Thus, the controller has a good presentation of what is in his area of responsibility. The size of the aircraft alone does not determine the size of the target on the scope. The size of the blip is determined by how good a reflector the target is. Turning propellers, amount of metal skin, and densities of the aircraft frame and engines, plus the attitude and distance in relation to the antenna, will determine the quality of the reflected image. All moving targets show as thin rectangles with their long sides perpendicular to the sweep. It should be noted that radar signals travel in straight lines until they reach a reflecting surface and are returned in a straight line. Thus, radar coverage is limited to line of sight and is unable to see over the horizon or behind mountainous terrain. The radars used in air traffic control are designed with specific jobs in mind. For example, air route surveillance radars, ARSRs, which monitor en route aircraft, have to see further than terminal radars. Therefore, the ARSR antennas rotate slowly, allowing more time to detect aircraft at longer distances. The radar systems used for terminal area control are called airport surveillance radars, ASRs. These rotate at higher speeds, giving a faster update of targets over shorter ranges. The only trouble is that both of these high-performance radar types often see too much for air traffic control purposes. The systems normally see the stationary objects in the paths of its beams, such as buildings, earth surfaces, trees, and the like. This so-called ground clutter blocks up the scope and makes moving targets impossible to distinguish from the clutter. Therefore, both ARSRs and ASRs have electronic circuitry called Moving Target Indicator. The Moving Target Indicator, or MTI, is a kind of electronic screen which cancels out targets that don't move, thus eliminating most of the clutter which makes moving targets hard to see. MTI has an unfortunate characteristic which sometimes limits its effectiveness. When an aircraft is flying on a course which will keep it perpendicular to the antenna, its range is constant, and MTI interprets this as a stationary target, thus canceling it. Controllers sometimes ask a pilot to vary the heading slightly because a few degrees course change will overcome this inherent deficiency in MTI. Of course, uncontrolled aircraft entering this condition represent a special hazard. The controller, not seeing a target, cannot issue radar traffic information to controlled aircraft. Although this is a relatively infrequent occurrence, it is a good reason for continued vigilance of other traffic, even though the aircraft is in radar contact. The air traffic control radars just described are called primary radars, in that they display reflected signals originally transmitted from the ground. When the word radar is used in air traffic control, it also refers to a secondary type of radar, known as the Air Traffic Control Radar Beacon System, and often referred to as radar beacon. Radar beacon is a separate system, operated with primary radars. The radar beacon system requires an interrogator on the ground, a transponder in the aircraft, and a decoder unit at the radar controller's scope. The interrogator is similar to the primary radar transmitter receiver in that it sends out short pulses of energy. The difference is that the interrogator sends out discrete pairs of signals which operate like an electronic combination lock. If the right pair is received by a transponder, it responds with a coded signal. Like all electronic equipment, transponders should meet minimum performance requirements in order to work properly in the system. Likewise, transponders should be maintained regularly to assure their operation. Radar beacon has several advantages. It supplements the primary return so it can be seen as a useful target under otherwise poor radar situations. It allows identification of transponder-equipped aircraft even in dense traffic, thus improving and speeding up control. Recent developments in the system displays essential altitude information on the scope. Radar beacon works like this. The interrogator sends out signals that are received by transponders operating in the appropriate code. When the transponder is triggered, it responds with coded reply pulses, which give certain information about the aircraft. The returned signal is decoded, reprocessed, and then displayed as distinctive information on the controller's radar scope.
Aztec 377, Miami approach. Squawk 1200, ident, over.
The controller can make a positive identification of a target on the scope by requesting the pilot to select the correct code and activate his ident button.
Aztec 377, radar contact 10 miles west of Miami International.
Transponder targets are always distinguished by 1 or 2 slashes or bars. The slash nearest the scope center shows the actual location of the aircraft, and the other is used for identification purposes. Although most centers and terminals use 64 codes, today's standard approved transponders have a capacity for 4,096 different code replies to allow for expansion and discrete code assignment. Pilots should keep the transponder operating on the appropriate code at all times while flying either VFR or IFR, unless advised otherwise by air traffic control. Then the ground-based interrogator can trigger the transponder, giving the controllers a positive return. Code 7600 is allocated for radio failure and 7700 for aircraft emergencies. Use of IFR codes in the ATC system is dependent upon the phase of flight, arrivals, departures, en route, and certain special uses. Air traffic controllers will assign the appropriate IFR code. In order to understand how radars work, let's put it all together.
Clear.
Look at air traffic control radar from the standpoint of a typical pilot in a normal kind of operation.
Roanoke ground control, Cherokee 4852 Sierra on the east ramp. IFR to Atlanta, request taxi instructions.
Cherokee 4852 Sierra, Roanoke ground, taxi to runway 23, wind 180 degrees 5, altitude.
3015, advise and ready, copy, clearance, over.
Roger, go ahead.
Cherokee 4852 Sierra,
Clear at Atlanta Airport, Victor 16, Victor 35.
Victor 20, maintain 8,000. Departure control frequency will be 126.9er, squawk 1000, just before departure.
Cherokee 52 Sierra.
Ward Mitchell has filed IFR to Atlanta, Georgia. His Cherokee is equipped with a 4096 transponder with automatic altitude reporting capability. He sets the transponder to the standby position on code 1000 and will switch it on just before takeoff as directed by ground control.
Piedmont 74, taxiing position at hold. Cherokee 52 Sierra, contact departure control.
Once the tower changed Cherokee 52 Sierra to departure control, responsibility goes to the departure controller, who closely monitors the departing aircraft.
Cherokee 52 Sierra, Roanoke departure control, radar contact.
Right turn, climb on course. Traffic 1 o'clock, 4 miles eastbound, over.
Mitchell's aircraft is assigned code 1000. Other codes might be assigned if operationally desirable. Say, if a special code is used for interfacility handoff. When the aircraft exits the terminal control area, the departure controller hands off the control responsibility to an en route controller in an air route traffic control center, which primarily utilize the long-range ARSRs mentioned earlier.
Cherokee 5-2 Sierra, squawk 1100.
Cherokee 5-2 Sierra, roger.
Washington Center, Roanoke. Departure control handoff 76.
Washington Center, Roanoke, go ahead.
8 miles southwest of Roanoke, Cherokee 5-2 Sierra, out of 6,004, 8,000. Your code.
Cherokee 4852 Sierra's radar contact. Maintain 8,000. Kilo Delta.
Cherokee 5-2 Sierra, continue climb down to maintain 8,000. Cherokee 5-2 Sierra, roger.
Cherokee 4852 Sierra, Washington Center, ident code 1100, report reaching 8,000.
Cherokee 5-2 Sierra, roger.
Well, now that we're en route, we can relax a little.
Yeah, but we still have to watch out for other aircraft.
A controller, either at a terminal or en route facility, may be controlling a number of aircraft simultaneously in his airspace, so may not be able to give his undivided attention to any one aircraft. And of course, the fact of radar surveillance does not decrease the pilot's responsibilities to see and avoid other aircraft. As stated earlier, uncontrolled aircraft may not be seen at all times, and radio frequency congestion or workload may prevent the controller from advising of unknown traffic. The control responsibility en route is handed off from one sector to another within the center and to another center after a brief period of dual surveillance while the radar handoff is being effected.
Cherokee 5-2 Sierra, traffic 10 o'clock, 3 miles westbound.
Cherokee 5-2 Sierra. I have them inside below us. Thank you.
A pilot of a radar-identified aircraft in an IFR flight clearance does not have to make a specific request for radar traffic advisories. Aircraft operating VFR may request this service, but work and communication loads will determine whether or not the controller can provide it. Whether operating IFR or VFR, the extent to which radar advisories are issued is dependent on many factors, such as controller workload, radar limitations, traffic volume, and communications congestion. A flight to Atlanta demonstrates another aspect of radar control, which is growing in importance. Atlanta is one of an increasing number of terminals utilizing FAA's Automated Radar Terminal System, called ARTS. What ARTS does is harness the beacon radar system to computer data processing equipment. Each transponder-equipped aircraft with an altitude digitizer feeds its signals to the system where the computer decodes, processes, and automatically displays flight information using numbers, letters, and symbols that associate with the aircraft's target on the controller's scope. Automatic altitude reporting capability adds a new dimension to the information available to the controller.
Line of flight service?
Automatic readout of an aircraft's altimeter enables the controller to monitor the altitude of properly equipped aircraft. This reduces time-consuming voice communications and increases the efficiency of the system.
Cherokee 4852 Sierra, Atlanta approach control, radar contact. Maintain your present heading for vectors to the 27 right final approach course.
Since the proper code was selected, the transponder information is automatically transmitted for the ARTS system. However, the altitude reporting switch was activated at Roanoke. ARTS is operational in many terminal areas, and aircraft equipped with the automatic altitude reporting capability are receiving full benefit from this type of facility. Previously, the controller had to make a mental association between target and data. Now, both pilot and controller can concentrate on the job of bringing planes in for safe landings. Observing radar in air traffic control under ideal conditions is one thing, but one must also consider the less than ideal weather, when radar control may be even more important. Rain, snow, or other climatic conditions affect radar signals. Rain, for example, creates a precipitation return because the radar signal is reflected off the raindrops. In order to counter this, ATC radars have a means of changing the antenna polarization to reduce the size and intensity of these returns. In most cases, they can be eliminated or reduced to a mosaic, which allows the aircraft targets to remain identified as they pass through the area of precipitation. Infrequently, because of shape or intensity of the precipitation, radar targets will be obliterated and identity cannot be maintained. However, beacon targets can be monitored in such cases since they are virtually unaffected by precipitation. As good as ATC radars are, continued radar contact is not assured in every situation. But the pilot will be informed when radar contact is lost. For example, when mountainous terrain shields transmission in a straight line between antenna and aircraft, radar coverage is impossible. The phenomenon which presents a more difficult situation is called anomalous propagation, or AP for short. This phenomenon invariably occurs in clear weather when temperature inversion or rapidly changing atmospheric conditions trap layers of warm or moist air in a way that allows radar beams to be bent. When the temperature gradient traps a layer of moist air under dry air, some of the radar signal is deflected away from the more dense dry air, thus possibly picking up targets beyond the horizon. When the dry air is trapped below a layer of moist air, some of the radar signal may be deflected away from the Earth, so that even relatively close targets go undetected. At times, the anomalous propagation becomes so prevalent that the controller sees dozens or even thousands of targets. Controllers often call these targets angels, although devils might be much more appropriate. Anomalous propagations are relatively short-lived and usually disappear as rapidly as they appear when the temperature of the air changes. They seem to occur primarily with clear weather and no wind, near sunrise and sunset. Radar's present sensitivity sometimes plays other tricks on controllers. Flights of birds will sometimes register as bright targets. Some experts believe most of the angels seen on scopes are actually radar detections of flights of birds. In any event, when there are more targets than can be positively identified, radar control becomes difficult or impossible. Then, too, anything as complex and sophisticated as air traffic control radars are subject to malfunction. Backup and redundancy are built into the systems. For example, if a transmitter circuit is lost, a backup is available. One should keep in mind that radar limitations, although very real, are the exception rather than the rule. Today's radars are excellent, improving all the time and generally are very reliable. But there's another aspect of radar that we haven't considered: the use of radar in abnormal situations. Take, for example, the experienced pilot Jim Ferguson, flying IFR from Miami to Key West.
Miami Center, this is Travel Air 1309er Zulu, over.
Miami Center, this is Travel Air 309 Zulu. Do you read me, over?
In radio failure, a transponder can be used as a radio link.
I can't seem to contact Miami Center.
Does that mean our radio is dead?
Well, I don't know, but I'm going to assume that it is.
The transponder code 7600 mentioned earlier is set aside for radio failure. The controller, noticing the loss of the en route transponder return, turns on code 7600 to determine if there is radio failure. The radio failure code, once selected by the controller, will cause the double slash to reappear, telling the controller that the aircraft is experiencing complete or partial radio failure.
Travel Air 1309er Zulu, this is Miami Center. Understand you have radio failure. If you hear me, ident. Travel Air 09 Zulu, Miami Center. Received your ident. We'll continue radar control. Proceed as cleared. Maintain 4,000. If you understand, ident.
Radar is an invaluable aid when a pilot is lost or in an emergency and must be located rapidly.
Travel Air 09 Zulu, your position 15 miles northeast of Key West, VOR. We'll advise Key West Tower of your arrival.
Radar is by no means a panacea, and it isn't perfect, but it's a mighty good feeling to have it along.
Travel Air 09 Zulu, cleared for VOR approach to the Key West International Airport. Upon leaving 4,000, ident. Travel Air 1309 Zulu, this is Miami Center. Key West Tower advises cleared to land runway 9er. Wind 100 degrees at 8. Altimeter 3015. Monitor tower frequency 118.2.
Air traffic control radar is doing the important job of keeping traffic moving and assisting the pilot during emergencies.
Roanoke Approach Control, this is Cessna 2666 Lima, approximately 30 miles east, VFR. Request your weather. Over.
Cessna 266 Lima, Roanoke Approach Control. Roanoke weather measured 4,000 broken, visibility 5 haze. Wind 160 degrees at 8, altimeter 3010. Visibility lower south.
Cessna 2666 Lima, roger. I'm at 2,500.
It's getting pretty hazy. Request radar assistance for Roanoke.
Cessna 66 Lima, are you transponder equipped?
Cessna 66 Lima, negative, no transponder.
Cessna 66 Lima, I show no radar target 30 miles east.
You may be below radar coverage. Can you climb to a higher altitude and maintain VFR?
Cessna 66 Lima, affirmative. I can make it to about 3,000 and maintain. Roger. Turning to 330.
Cessna 66 Lima, Roanoke Approach Control, radar contact 25 miles southeast of the Roanoke Airport.
It's a good feeling to know you're on radar, that radar's all-seeing eye has found you and will help guide you to your destination. But then radar has been around so long that we take it for granted. The mystery which once surrounded radar has gone, and the giant turning antennas and bright scopes are now commonplace.
6 northeast.
Radar is great. We've learned to depend on it. But the problem is that, like so many good things, we tend to become over-dependent on it. The result sometimes is a compromising situation where radar can't help due to its limitations. Admittedly, we don't yet have full coverage at all altitudes and in all areas.
Maintain VFR.
Cessna 266 Lima, roger. Report reaching 3,000. Maintain VFR.
A low ceiling, mountainous terrain, and an anxious VFR pilot.
Cessna 66 Lima, Roanoke Approach Control. Cessna 66 Lima, Roanoke Approach Control. Do you hear me? Over.
Cessna 66 Lima, affirmative. Just approaching 3,000, heading 270.
Cessna 66 Lima, roger, thank you. Cessna 66 Lima, I'm starting to paint a target 25 miles southeast. Turn right heading 330 for radar identification.
Cessna 66 Lima.
And as good as radars used in air traffic control generally are, they are not perfect. The point is that radar controllers can't guarantee to get you in every time. A pilot's responsibilities still hold, even with assistance. Fortunately, we don't all have to become radar experts in order to use its services. Often, radar can help us in spite of our lack of information. However, understanding the fundamentals of radar can enable us to utilize it more fully and intelligently. The kind of radar equipment used in air traffic control can be described in simplest terms as a high-frequency radio transmitter broadcasting high-energy short radio waves through a rotating antenna. The name radar comes from the World War II acronym for Radio Detection and Ranging. Radar works on an echo principle. So much energy or power is transmitted that when it strikes a radio reflective surface, enough of the energy bounces back to the antenna to be picked up, amplified, and fed to a display called a scope, where the signal registers as a bright blip or radar target. The scope is a cathode ray tube similar to a television tube. The type of radar most useful for air traffic control is designed so that the signals can travel a two-way street. Therefore, the transmissions are made by alternately turning the transmitter on and off repeatedly in mere fractions of seconds. The return echoes are received and processed during the intervals between transmissions. This allows the system to utilize one antenna for both sending and receiving and still look at a number of targets simultaneously. The reason that a radar can show distances so accurately is that the signals travel at the speed of light, so that the length of time it takes for an echo to return